All right, in this lesson, we're going to look at bond energies, which is yet another method to determine the delta H, or the change in enthalpy of a certain reaction. In this case, we're using bond energy. So what is bond energy? So each bond breaking is an endothermic process, and bonds forming is an exothermic process, right? So the enthalpy of a reaction can be calculated using the bond energy, the energy that's required to break a bond or form a bond. Now, in standard enthalpy of formation, when we looked at those videos, we learned that when a reaction occurs, the bonds of those reactants have to break apart, and then they have to reform to form the products, right? So the energy calculated for those bonds breaking and the energy that's required for those bonds forming can be used to calculate the change in energy of that particular reaction. That's what this whole video is all about. So the formula for this is as follows. So again, we're trying to find delta H, and in order to do that, we're going to take a look at the sum of, and remember this symbol means sum of, the energy of the bonds broken. So we need all of those reactants, those bonds to break. So the total energy required for those bonds to break minus the sum of the energy of bonds formed. So these are the bonds in our products that are being formed. Now, another way to express the same formula is, again, we're trying to find delta H, and we're going to take a look at the sum of N, which is the number of moles, of D, which is the bond energy of bonds broken, minus the sum of the moles of the bonds formed. Moles times the bond energy of the bonds formed. So these are the exact same formula, just expressed in two different ways. In the first formula, you have energy just written as a total. In the second one, you're just splitting those two up. But in both cases, we have to take into account the number of moles there are in that particular reaction of those particular molecules. And when we do those specific examples, you can see where those come into play. So as we said, bond energy can be used to calculate delta H, but this is only an estimate because bond energies are average values from the same bond in a number of different molecules. What I mean by that is, so we're going to take a look at a chart very soon, right? This is what the chart looks like, and we're going to need to reference this quite often whenever you're working with bond energies, because this is a list of those bond energies. These are all average values of the energy required to break or form this particular bond, right? So if I have a carbon-hydrogen bond, what they've done is they've taken different molecules with carbon-hydrogen bonds in it, and they've figured out how much energy is required to break those or form those, right? All of those energies are then averaged together to get this particular number, right? So all of these numbers are actually averages and not super exact, right? Which is why when we get the answer of delta H from bond energy, you will see that it is an approximation and not an exact number, right? And when we use some of those other methods, you might get a more reliable answer. But in some scenarios, all you might have is bond energy. And based on that, you'd have to figure out the delta H value. Okay, before summing, the bond energies must be multiplied by the number of that bond present and the coefficient from the balanced chemical equation, right? And remember, in that second formula that I wrote out, there's a small n, which is the number of moles, that can account for the coefficient, right? We already talked about that. But when you're multiplying, you also have to take into account the bond, the number of that bond there is in that molecule. Let me give you an example. So if we're taking a look at, let's say, CH4. Okay, and when you balance the reaction with CH4 in it, let's say you have a coefficient of 3. The first thing that I'm going to need to do, which I'm going to talk about in the next point, is that we have to draw out this particular molecule, right? And because I've reviewed my Lewis structures, I know that the structure for CH4 looks like this. Now you'll notice that there's only one type of bond in this molecule, and that bond is a carbon-hydrogen bond. You might have scenarios where you have more than one type of bond, and that's totally fine. You'll just have to separate those into each different type of bond, right? In our case, we're just looking at the carbon-hydrogen bond at the moment. So when I'm taking a look at this scenario of 3 CH4s, when I'm trying to find the total bond energy, I'm going to first take into account the coefficient, right? So 3 moles of CH4, right? And then I want to take into account how many of those bonds I have in this molecule. If I'm looking at a carbon-hydrogen bond, I've got 1, 2, 3, and 4, right? I've got 4 different CH bonds. So I'm going to multiply that by 4, and then I'm going to multiply by the bond energy, which is 413. And all of the bond energies are measured in kilojoules per mole, right? So when I'm multiplying, or when I'm trying to find the total energy of the bond broken or formed, I'm taking a look at this sort of scenario. I'm multiplying by the coefficient and by how many of those bonds there are in that molecule, and then multiplying by the bond energy. Only then can we be able to find the delta H of that particular, or the change in enthalpy of that particular reaction. Just moving back to this particular chart right here, a few things for you to note. As I mentioned, this is all measured in kilojoules per mole. So each bond energy, for example, the N and O double bond, that bond energy is 607 kilojoules per mole. They are separated by single bond or multiple bonds. And one thing to pay special attention to, if you see here, the carbon and oxygen with a double bond, this particular bond usually has a bond energy of 745 kilojoules per mole. But you'll see that there's an asterisk here, and down here it says whenever you're talking about carbon dioxide, the carbon and oxygen, the double bond, that double bond has a bond energy of 799. And this is very important because in a lot of cases that we're going to see, and you'll notice this in the examples that we're going to do, we work with carbon dioxide quite a bit. So in those scenarios, when you're trying to find the bond energy of the carbon and oxygen double bond, make sure that you're using 799 because we're talking about carbon dioxide, right? In any other situation, a carbon and an oxygen with a double bond in between them would be 745 kilojoules per mole. But in carbon dioxide, it's 799. Just keep that in mind. Okay, so we learned how to calculate the total bond energy of a bond broken or formed. So when writing the balanced equation, the structures of each species must be drawn to determine the types of bonds present, right? So this is where you have to make sure you review your Lewis structures before we do the practice for this particular lesson, right? It's very important that we review that because we get into the habit of drawing these Lewis structures because a lot of times you might not be given the structures, but rather just the reactants and the products, right? So you'll have to draw it out to see what bonds there are and how many of it there are, and then you can do those calculations. If you don't get that right, your answer might be wrong. Also, last thing, so multiple bonds, so those are your double bonds or your triple bonds, have larger bond energies than single bonds, right? So the length of the bond shortens as the number of bond increases. So a triple bond is the shortest of the 3 bonds, the double bond is a little bit longer, and the single bond is longest.